When the Space Shuttle program, seen here with Atlantis, was retired in 2011, the United States lost its domestic capacity to send humans into orbit. NASA had to purchase seats aboard the Russian Soyuz system at a cost of up to $80 million per astronaut, simply to maintain a presence on the International Space Station. For decades, the aerospace industry operated almost entirely on cost-plus contracting. Under the system, governments paid companies for all their expenses, plus a guaranteed profit percentage. This removed the financial incentive to work quickly or reduce manufacturing costs. The bottleneck holding back human spaceflight in the early 2000s was this inefficient economic model, which rewarded stagnation and penalized risk. When Elon Musk founded SpaceX in 2002, the initial strategy bypassed exotic propulsion or experimental physics. The mandate was purely operational, figuring out the exact processes required to drastically lower the unit cost of reaching orbit. By bringing 70 to 80% of manufacturing in-house, the company bypassed traditional supply chains and established cost per kilogram as a primary design objective. Putting that model into practice required aggressive physical testing. The early development of the Falcon 1 rocket was marked by back-to-back launch failures that pushed the startup to the edge of financial collapse. That streak ended when a Falcon 1 finally reached Earth orbit, becoming the first privately developed liquid fuel rocket to achieve the milestone. That single flight validated the vertically integrated business model. It proved that a centralized, iteration-heavy company could indeed deliver massive payloads to space, providing the leverage needed to scale operations. Further growth was secured by NASA's Commercial Crew and Cargo programs. NASA awarded fixed-price contracts to private vendors, eventually providing SpaceX with a $3.1 billion lifeline to develop orbital transportation services. This funding financed the creation of the Falcon 9. Its current iteration, the Block 5, is powered by 9 Merlin engines and serves as the primary workhorse of the commercial space industry today. Sitting atop the Falcon 9 is the Cargo Dragon spacecraft. Its design features a pressurized capsule for sensitive materials and an unpressurized trunk to support the vehicle during ascent. In 2012, Dragon became the first private spacecraft in history to deliver cargo to and from the International Space Station. Because NASA's investment was a fixed price, SpaceX absorbed all cost overruns. This structure forced the company to deliver results efficiently, proving the aerospace sector could function without the bloat of cost-plus contracts. To drive unit costs down even further, the hardware had to be recoverable. Achieving rapid reusability required a grueling, highly public period of trial and error testing. Returning an orbital-class booster intact means guiding a massive falling cylinder through atmospheric reentry at supersonic speeds. Titanium grid fins deploy from the top of the booster, acting as aerodynamic control surfaces to constantly adjust the rocket's trajectory as it falls. Moments before touchdown, the booster ignites a single engine, using a precise thrust vector to rapidly decelerate into a controlled hover. The system proved operational in 2016, when a Falcon 9 first stage successfully landed at sea on the Of Course I Still Love You droneship. Recovering these boosters meant launch vehicles could be serviced, refueled, and flown again. Rockets transitioned from disposable, single-use hardware into commercial fleet assets. By 2018, the architecture scaled up with the debut of the Falcon Heavy. Combining 3 cores and 27 engines, it provides over 5 million pounds of thrust at liftoff. With cargo and heavy lift operational, the next mandate under NASA's Commercial Crew program was the most complex, rating the Dragon 2 capsule to carry human passengers. Human rating required rigorous fault tolerance and a completely new environmental control and life support system to regulate cabin pressure, manage the temperature, and filter trace contaminants. After years of development and simulation, NASA astronauts Bob Behnken and Doug Hurley flew the Demo 2 mission in 2020, successfully docking their Crew Dragon capsule at the International Space Station. Their arrival ended a 9-year period relying on foreign systems. It confirmed a commercial entity could safely manage the extreme demands of human spaceflight. Today, Falcon 9 launches and booster recoveries are routine, driving down operational costs enough to support the deployment of the massive Starlink satellite constellation. But the manufacturing infrastructure located at Starbase, Texas, is built for a much larger vehicle. This is Starship. It is a super-heavy two-stage system designed from the ground up for full, rapid reusability and unprecedented payload mass. This architecture scales the lessons of the Falcon 9, attempting to apply rapid reusability to a vehicle capable of carrying hundreds of tons beyond Earth orbit. The Starship program is currently navigating its own high-risk testing phase out of Boca Chica. Pushing these massive prototypes to their physical limits often results in highly visible, destructive failures, the exact same trial-by-fire methodology that built the Falcon 1. Establishing a multiplanetary presence requires continuous physical flight testing. It is a harsh, mechanical process that can only be solved on the launch pad. SpaceX maintains its momentum through a relentless cycle of building, breaking, and refining hardware in real time. By abandoning traditional contracting and reinventing the operating model, SpaceX turned near bankruptcy into an operational system that moves thousands of kilograms to orbit every week.